Another addition mechanism we need to consider for alkenes is dihydroxylation. So if we write that out, what does that imply to us? Well, di meaning two, and hydroxy is OH. So we're going to be adding two OH groups. And essentially, if we wanted to sort of make this a very generic little schematic here, we could say this is what we'll be doing. Now, that product is called a glycol or a diol. Diol is the more systematic name. Sometimes you'll see in common descriptions glycol used here. This would be ethylene glycol like you'd find in antifreeze. We have two mechanisms to do this based on stereochemistry. We can have anti-dihydroxylation. That's going to be a two-step mechanism. Or we can talk about syn-dihydroxylation, which is a one-step mechanism. And so we'll explore both of those here as we go forward. First, the anti-mechanism. This occurs in a two-step process. And so that we can look at stereochemistry, I'm going to use a ring shape. And so we'll look here at something like cyclohexene. The first step is to treat this with a peroxy acid. So a peroxy acid has the formula of RCO3H. It's got an extra oxygen compared to a normal carboxylic acid. In some books, this reaction by itself is considered a second or a whole separate reaction. This produces an epoxy group. And so this is going to produce for us an oxygen bridge like this. Now, once we've produced that, the second step of our dihydroxylation is to do an acid-catalyzed ring opening. And so usually you'll just see this written as H3O+, just some sort of aqueous acid. It doesn't particularly matter what's going on here. But just like we saw in the case of the bromonium ion intermediate and our halogenation mechanism, the fact that that epoxy oxygen is on one side of the ring or the other, I've drawn it forward, I could have drawn it backwards, that means that when water comes to attack, it will likely attack from the opposite side. And so what I'll end up with is the anti-addition, where my one OH, that's the original oxygen that I've been following all along, the one that came from the peroxy acid, is on one side of the ring, and the other OH is on the other side of the ring. And if I color code these, this would be the red oxygen that I got here, and this one would be my blue oxygen that came from the peroxy acid. The other mechanism that's the syn version here, syn-dihydroxylation, is a one-step, and the details on this reaction are a little bit messy to look at, but what it amounts to is that we end up treating our molecule with osmium tetroxide, OSO4. Osmium tetroxide is a really cool looking compound that has osmium as a really big center connected to 4 oxygens by double bonds. And what ends up happening is that these 2 of these oxygens will become the oxygens that get attached. And since they're both coming from the same osmium center, they're both coming from the same molecule in solution, we then end up with, at the end of the day, 2 oxygens facing the same direction. And again, I could have drawn that either way, 2 oxygens forward or 2 oxygens backwards. The full details of how this works are shown in the book, but the important part to notice here is 2 different mechanisms giving us 2 different stereochemistries. Anytime I'm dealing with a peroxy acid anything that says RCO3H or a particular one that might be listed, I would have that peroxy acid name in its naming. That's going to give me my anti-product. If I'm using osmium tetroxide, that gives me syn dihydroxylation.